how much material I have, but we'll see how that goes. Today is actually the last material that comes from my book, and then I have some other material for next week about basics of statistical learning and how that relates to things that we've seen up to that point, and then that'll be it. So, without further ado, okay. We've seen the singular value decomposition in the context of least squares problems, and you know that my advisor Gene Golub's main achievement was to come up with the first algorithm for it. If it wasn't just him, it's really the Golub-Kahan algorithm that was the first. Kahan was I think he's still alive, retired professor at Berkeley who has written a lot about floating point arithmetic and issues related to that. So when I introduced the SVD earlier, I didn't really have enough concepts presented to explain to you how Vsvd can be computed. But now that you've been exposed to algorithms for computing eigenvalues, we can make use of those to compute Vsvd. Okay. All right, so just a refresher, what is Vsvd? We'll assume that the matrix A is real, not necessarily square. So it has this decomposition. U and V are orthogonal matrices, so U is M by M, V is N by N. Sigma is diagonal, same size as A. Diagonal entries are the singular values. We assume they're ordered from largest to smallest. These are all non-negative real numbers. Okay, so those are singular values, and the columns of U and V are called the left and right singular vectors. All right. And as we saw, it has a lot of applications, mostly related to least squares. It gives you the null space and range of a matrix, the rank of a matrix, its two-norm condition number. Low rank approximations are easily obtained from the SVD, and so on. But now there's a matter of how do we actually get it? What is a practical algorithm for obtaining the SVD? Okay. And why was Golub so proud of his algorithm that he dubbed himself Professor SVD on his license plate? Now, since I'm the inventor of Krylov subspace spectral, or KSS methods, I guess I should have something about those methods on as my license plate too, except I have such an uncool car that there's no way I could put a vanity plate on it. So, oh well. All right. So, if we break up U and V this way into their columns, then these columns have these relationships that if I multiply A with a right singular vector, then I get the corresponding left singular vector times the corresponding singular value. Now, if we assume that M is like greater than N, then we have an excess number of left singular vectors. So the J would only cover the first N. But the number of singular values is always the minimum of M and N anyway. So these indices will always be valid. If I take a left singular vector multiplied by the transpose, then I get the corresponding right singular vector times the corresponding singular value. So what I can do is, if I take this equation and I multiply by both sides by A transpose, then I get this on the left side. On the right side, I'll have A transpose Uj, but then I use this equation on the right side of this one, and I'll get sigma squared Vj. So by putting these two equations together, what we have here is an eigenvalue-eigenvector relationship that the right singular vectors, the columns of V, are eigenvectors of the n by n matrix A transpose A, and the eigenvalues are the squares of the singular values. And A transpose A is a symmetric matrix. So this relationship alone gives us at least one way to proceed in getting the SVD. So this serves as at least a starting point in coming up with a practical algorithm. But first, to come up with one that is simple but not maybe impractical. So here's what you can do. Since this is a symmetric matrix and we have a symmetric eigenvalue problem, then you go ahead and apply what I covered last time, a symmetric QR algorithm to A transpose A. And that will give you a short decomposition of A transpose A. So you have your orthogonal matrix V, a diagonal matrix here, and then V transpose. Because in the short decomposition, the columns of this matrix are the eigenvectors of a matrix you're working on, so A transpose A. And we see from this relationship, those eigenvectors are the right singular vectors. So all we have to do is take a square root of these diagonal entries, because this would be like sigma squared in a way. And we'll have a singular values, and then we have a right singular vectors. So the only thing that we would be missing is the set of left singular vectors. But fortunately, we have an easy way of getting those. Once we have sigma and V, we go back up here. So I can take my right singular vectors that I get from a short decomposition, multiplied by A, and I get whatever vectors I get, I normalize them, or I can divide by the singular values I have, same thing, and that would give me the left singular vectors. All right. Now, there's a mention here of QR with column pivoting. There's something I actually haven't covered. That's a variation of, just as we have Gaussian elimination with pivoting, it's row interchanges. There's also a variation of QR factorization where you have column interchanges for rank deficient matrices. The purpose of that is to get everything in the proper order, because the SVD, as written here, one aspect of it is that the columns of U and V are ordered according to the size of the singular values. Okay, but in any case, if we just do symmetric QR algorithms, so what we saw last time on A transpose A, that gives us sigma and V, multiplying columns of V by A gives us the columns of U. Okay, and one other point I forgot to mention. I should make that clear here. Let's suppose, again, M and N can have any relationship. N could be less than, greater than, or equal to N. But if we assume that M is greater than N, this gives us the N columns of V. This would give us N of the columns of U, but it doesn't give us the rest of U. The rest of the columns of U come from, they have to be orthogonal to all the columns that we have. QR of column pivoting is useful for that too. So it has the effect of basically completing the entire vector space Rm, so that we have all the columns of U. If I only did this and not the QR of column pivoting, then I would have what's called the economy size SVD. Okay. So we could just stop here and say, okay, well, we have a way of computing both sets of singular vectors and also the singular values. What more is there to do? Well, this numerical analysis. There's always more to do. Because we have round-off error. When you're computing A transpose A explicitly, you're going to have floating-point arithmetic errors or round-off errors. So that is a vital loss of information about the entries of A. So what you're really doing is, oh man, a faculty meeting on Friday. Ugh, kill me now. So I just totally forgot we had that coming up. It's a nice way to ruin Fridays, but anyway. Okay. I probably should not have immortalized that on YouTube, but whatever, it's true. Okay. Well, maybe someday some of you will learn firsthand what I'm talking about. So we're obtaining singular values and singular vectors from a less accurate version of A, effectively, because of the round-off error incurred here. So we like to find a way to get the singular value decomposition without explicitly forming A transpose A. So just as was done in the eigenvalue algorithm, in the QR algorithm, basically finding ways to fake it, like by relying on things such as the implicit Q theorem, we could do the same thing with the SVD. We can implicitly apply the symmetric QR algorithm to A transpose A without actually forming A transpose A. Okay. Okay. So how are we going to do that? So what we can do is we can apply householder reflections to A coming from both the left and the right. So the ones on the applied on the left will basically behave similar to what's done in the QR factorization, zeroing out all the entries below the diagonal. And then we can also apply householder reflections on the right to zero out entries of these rows. So we keep the diagonal and we keep the first super diagonal and zero out everything else. So what would happen is, suppose the first reflection I apply on the left zeroes out everything in the first column. Then when I use the first reflection on the right to zero out everything in this row, that's going to affect columns 2 through n. It will not touch the first column. Therefore, all the entries that I zeroed from transformations over here will not be undone by whatever reflections I apply over here. Whereas if I was trying to wipe out everything above and below the diagonal, each transformations would be stepping on each other's toes. But this here they can be done without interfering with each other. So what we get is a matrix that is upper bidiagonal. So we have two diagonals that are non-zero, and it's upper bidiagonal because we preserve a diagonal and the one above it. Okay. Now, so that gives us, so if we look at B transpose B, that is symmetric, and it's also tridiagonal because of B being bidiagonal. So the reason why we're doing this is, what is, well, okay, someone tell me, in the symmetric QR algorithm, what is the very first thing that is done to the matrix A? That I just covered on Monday.
We make it a tridiagonal matrix.
Yeah, so you're performing, well, so in an unsymmetric case, it'd be a Hessenberg reduction, but in a symmetric case, that ends up being tridiagonal. So yes, it's a tridiagonal reduction. So that's what we're doing here. So instead of forming A transpose A and reducing it to tridiagonal form, we apply household reflections to A, only A, to make it bidiagonal, and then we sneakily get T. Now, the reflections applied here from V1 are those are the transformations that we would be using if we were actually applying a symmetric QR algorithm to A transpose A. But we're just applying them to A instead. And what you can do, and actually, I don't know, I can never remember which problems I assign. Let me check real quick. From this section, oh, just 1 and 2. Okay. So one of the problems I did assign from this section, if it's only one other, is actually computing the entries of T in terms of the entries of B. So basically, you're carrying out this matrix product and getting formulas for these entries, and they're not very complicated formulas because there's mostly 0 entries. So it's not hard to get. It's very easy to get a hold of individual entries of T in terms of those of B. Okay. All right. Now what? So what we could do is go ahead and form T and apply the symmetric Q algorithm to it. But again, we get loss of information from actually computing these entries. So instead, we want to implicitly apply the symmetric Q algorithm to T by working only on B itself. So here's what we can do. Okay. So we don't compute all of T. We do compute its first column. Now, T is a tridiagonal matrix. Its first column is only going to have 2 non-zero entries. So we figure out the shift that the symmetric QR algorithm would give us, and that would come from the lower right 2x2 block of T. So we're only computing a handful of entries. Now, yes, we are incurring some information loss from those individual entries. So that unfortunately that's the best we can do. But it's still better than if we were to compute T in its entirety and then only work with it. Okay. So what we do is we figure out if we were going to apply the symmetric QR algorithm to T, therefore compute the QR factorization of T minus the shift, what would the first Givens rotation be? So we'll go ahead and compute that. So we'll call that G1 transpose. Okay. Then what we do is we don't form T and apply G1 to it. We apply it as a column rotation to B. Now, why do we do that? Because remember, if we were actually applying a symmetric QR algorithm to A transpose A, or to B transpose B, that would give us the right singular vectors. That would lead to the columns of V. So in other words, from transformations that are applied on the right. So that's what we're doing here as part of that transformation. Now, what happens is, okay. When we do that, remember, B is this matrix right here. It's upper bidiagonal. If we rotate the first 2 columns and we see where they're non-zero, we're going to get a non-zero entry right here in a 2-1 position because of this non-zero 2-2 entry here. So that wrecks the upper bidiagonal structure, which would then cause T, if we were to form it, to no longer be tridiagonal. Then what we do is we apply Given's row rotation on the left to rows 1 and 2, because we have this unwanted non-zero entry right here. By rotating rows 1 and 2 using D1, we can get rid of that entry. So now we no longer have any unwanted non-zero entries below a diagonal. But if I rotate rows 1 and 2 to zero out this entry where I'm hovering right here, that's going to wreck the upper bidiagonal structure in a different way. It's going to give me a new unwanted non-zero entry. Can anyone tell me where it would be? Rotating these two rows. So now each of the first two rows will be linear combinations of themselves.
Above F2?
Yes. Here, right here. Yeah, above F2. So in the 1-3 position, we'll get something that we don't want. Okay. So this is what we've done so far. Applied a Given's rotation on the right, then applied this one on the left to at least wipe out everything below a diagonal, but now we have that 1-3 entry that's a problem. I just realized my choice of notation, I've abbreviated Hattiesburg, but go figure. Okay. So what do we do about that? So now we have something we don't want right here. Now we apply a column rotation, columns 2 and 3, to use F1 to wipe out the bad entry here. Okay. But that also will cause a problem. That'll introduce an unwanted 0 in this position below D2. So row 3, column 2. So then what we can do, though, is continue this process. We keep, so it's basically a game of whack-a-mole. We have an unwanted non-zero entry pop up. We use alternating row and column rotations to wipe it out and introduce it somewhere else. So a mole pops up in another entry in the matrix, whack it, and then, but what happens is, look where the unwanted entries are. First, there's 2-1, then 1-3, then 3-2. It's going to bounce back and forth, but keep going down the matrix. Eventually, what you can do with these rotations is you chase it out the right side, to the lower right. So once you get all the way to the end of a matrix, the unwanted non-zero entry is gone, and B is upper bidiagonal once again. Diagonal. Okay. All right. Okay. So it's kind of a weird process. Questions up to this point? Okay. Now, all we were doing here is trying to fix the bidiagonal form we started with after applying G1 that messed it up. Now, why does that work for us? Because of the implicit Q theorem. So since G1 is a Given's rotation that would start the QR factorization of T if we were to form it, or not T, but T minus mu identity. Then all the column rotations that we use to make it upper bidiagonal again, that amounts to the same transformations that we would perform if we did form T explicitly and apply the symmetric QR algorithm to it with that same shift. So we're making sure that the transformation that we're applying has the same as the same first column. And the reason why that works is, after we apply G1 on the right, all the other rotations we apply on the right don't affect the first column. So if we were to take a product of all of these rotations, all of the G's, then the first column of that accumulated product would be the first column of G1. So we're coming up with a Hessenberg reduction, which is, because of symmetry, a tridiagonal reduction of T that has the same first column as the one that the actual symmetric QR algorithm applied to T minus mu I would be. Because they have the same first columns, by the implicit Q theorem, these transformations are essentially equal. So, in effect, we are applying a symmetric QR algorithm implicitly to T, but we're only working on B. And we're just using a few select entries of T to come up with a first transformation. All right. So now that we have a symmetric QR algorithm going, first the tridiagonal reduction of A transpose A, which is really the bidiagonal reduction of A to B. And now we know how to carry out the symmetric QR algorithm steps by applying transformations only to B. If we think about what the symmetric QR algorithm needs next, well, we have to detect decoupling. If we did form T explicitly, we would be looking for 0 entries on the subdiagonal. That would lead the eigenvalue problem to split and let us work on smaller matrices. So how do we detect that kind of decoupling if we are only working on B instead? So we have to know how to spot it. And fortunately, it's easy to do. So if any superdiagonal entry of our bidiagonal matrix B is small enough that we can essentially say it's 0, then we have decoupling, because every subdiagonal entry of T is a multiple of a superdiagonal entry of B. So if one of these superdiagonal entries of B, one of these becomes 0, that would cause a 0 subdiagonal entry of T. The other possibility is, what if a diagonal entry becomes 0? That also leads to decoupling. There's a bit of work to do in that case. But the point is, any 0 entry in B tells us that we have decoupling in T. And that allows us to work on smaller portions of B corresponding to working on smaller portions of T implicitly. All right. Okay, so eventually we reduce B to diagonal form. That would have the effect of also reducing T implicitly to diagonal form. And then the symmetric QR algorithm that we're faking is finished. So all of the household reflections that are multiplied on the left with A, so starting with these, the accumulation of all of these household or Gibbons rotations make up U, and the accumulated product of all of the household reflections or Gibbons rotations applied on the right of A, those make up V. The only thing that would be left is the eigenvalues, well, the singular values are the diagonal entries of B once we make it diagonal. The only thing left to do would be to order them, so we could just permute the rows and columns of B and also permute the columns of U and V to get everything in the right order. Now we could also get, since we had sensitivity results for eigenvalues, we have the same for singular values. Okay. Okay, I mentioned before, for example, there's a Wieland-Hoffman theorem that is about the sensitivity of eigenvalues for a symmetric matrix. There's also a result about individual eigenvalues are perturbed for a symmetric matrix. There are similar results for singular values. I won't get into details here, but I just want to mention that this relationship between the SVD and the symmetric QR algorithm can be used to establish those results. But one result that I do want to state, we have for symmetric eigenvalue problem, we have the okay. We have the Courant-Fischer Minimax theorem, and we have a similar result for singular values. So this says that the kth largest singular value of A comes from considering all subspaces all subspaces of Rn of dimension k and all subspaces T of Rm that have dimension k. And then we consider vectors in those subspaces, and this expression here. So we take the minimum of this quantity, and then over the subspaces S and T chosen, but then we maximize that over all possible subspaces of these dimensions, and that gets us the kth largest singular value. Now, equivalently, this is a simpler characterization here, that if we take all subspaces of Rn of dimension k, find a minimum in each subspace of norm of Ax over norm of x, and then take a maximum over all possible subspaces of that dimension, that also is the kth largest singular value of A. All right. All right. Wow, I've actually come to the end. All right. Well, I saw I only had a little more than 2 pages, so I had a feeling that the whole time would not be filled. Okay, so we see that household reflections and Gibbons rotations are highly versatile tools. We can compute QR factorization, eigenvalues, also singular values. One use of Gibbons rotations I did not cover is an alternative method for the symmetric eigenvalue problem. That you can, if you use Gibbons rotations on the left and right, like the same rotations on both sides, to zero out some off-diagonal entry of A, and you keep doing that repeatedly, you can whittle A down to diagonal form, and you can do this in whatever fashion you choose. That's called the Jacobi method for computing eigenvalues of a symmetric matrix. And in that setting, Gibbons rotations are actually referred to as Jacobi rotations, even though they're exactly the same thing. It turns out, though, these rotations were not invented by Gibbons. They were invented by Jacobi. I don't remember exactly how Gibbons' name got attached to them. Maybe it's because of how Gibbons chose to apply them for certain problems. But so anytime you need to zero an entry or a portion of a row or column, and do it using an orthogonal transformation, then that's where householder Gibbons comes in, and It is particularly convenient for similarity transformations because then you want to apply a certain matrix on the left if it has inverse on the right. Well, if it's orthogonal, the inverse is a transpose. So it's a lot easier to do by requiring orthogonality. Okay. Now, all right, so do we have any questions about this or about homework problems? I know a lot of you have been focused on the PDE test this week, but I know it doesn't apply to all of you. Or I've just fried your brains to a crisp. From a whole semester's worth of this. Oh, nothing at all? I just went out early. All right. Well, let's see. Today is April 7th. Okay, so well, it'll be actually exactly 1 month from today. That oh, sorry, Taylor. Okay. Oh, that didn't show up in the chat. Okay, that's weird. Okay. Oh, the meeting chat is muted. That's weird. I didn't want that. Okay. Not sure what to make of that. Okay. So yeah, so 1 month from today, and then that's when all the work is due. And so hopefully everybody can get everything in by then. Maybe able to allow a little bit of leeway past that point because that's the Friday before grades are due. And if I have too much happening at the last minute, that might make things difficult. But I guess it'll be an interesting weekend. At that point, we can all just pass out. So, okay. Well, then I'll stop recording here, and